Hi, in this video we are going to start chapter 9, the two proportions for the first sections. And for the last chapter, recall that we only did the hypothesis testing for one sample. But for this chapter, we focus on the inferences from the two samples. Inferential statistics is affirming about the conclusions for population parameters. This could be a proportion, a mean, standard deviation, or variance. But the first section for chapter 9, we focus on the two proportions. So just a quick recall again, from chapter 7, we estimate the values of the population parameters using the confidence interval. And then we make the testing, the claims about the population parameters from chapter 8. And now we focus on the testing about the claim for the two samples. Two independent proportion tests are used to compare the proportion in two unrelated groups. When we talk about the two independents, we are talking about two unrelated things, unrelated groups. And to conduct inference about the two population parameters, we must first determine the sampling distribution of the difference between the two parameters. Example, test the claim that the proportion of satisfied customer rate for AT&T Cellular is greater than the rate for T-Mobile. We can see that we have two groups of population here, the AT&T customer and the T-Mobile customer. So we compare them, we make the claim about the two population. That's why we focus on the two proportions in this case. Okay, so we will do the testing about the two population proportions and also constructing a confidence interval estimate of the difference between the two population proportions. Okay, let's say that we have two population 1 and 2. I label P1 is the population proportion of population 1, and then P2 is again the proportion. N1 is the sample size, N2 is also the sample size, but it's coming from the population 2. And X1 is the number of successes in the sample. And P hat is the sample proportion. Okay, so we use the notation P hat for the sample proportion. So P hat 1 is X1 over N1, and P hat 2 is X2 over N2. And Q1 is just a complement of P1, and again Q2 is 1 minus P2, P hat 2, and it's also the complement of P2. It should be P2, right, the typo. For the hypothesis testing, we compare the two population proportions. Then the null hypothesis is a statement of no difference, no change, or no effect against. The null hypothesis always involve the equal sign. So in this case, we compare about two proportions. So we let P1 and P2, they are equal first, and then we make the alternative hypothesis to be either two tails, left tail, or the right tail. So P1 may be different from P2. P1 is greater than P2, or P1 is less than P2 for the alternative hypothesis. Now, because the null hypothesis is assumed to be true, so the test assumes that P1 and P2 they are equal. If they are equal, if you subtract P2 on both sides, then P1 subtract P2. The difference should be 0 because they are equal. So there's no difference between them. So when you take the subtraction, you should get 0. Now we also need a point estimate of P, which is the population proportion, because we don't know the value of that. So the best point estimate of P is called a poor estimate of P. And we can find the P hat or the poor estimates just by adding the X1 and X2 together, which is the number of successes, and divide by the sample size of N1 and N2 adding together. And the best point estimate of the common proportion is obtained by pulling the two samples into one big sample. So that's why we call this is the poor estimate of P. Again, similar to chapter 8, you have to do some requirement check before you can do the claim, testing the claim. So the first requirement is that the sample proportions are from the two simple random samples and that they are independent. Again, the two groups must be unrelated or they are independent. And the samples are independent if the sample values selected from one population are not related or somehow naturally pair or match with the sample values selected from the other group. And after we check this requirement, make sure that from the two samples there are at least 5 successes and at least 5 failures. So we can check that by checking the inequality. So n1 times p hat 1. Make sure it's greater than or equal to 5. And also n1 of p hat, n2 p hat 2 is also greater than or equal to 5. So there are two parts. Part A, we focus on the p-value, and part B, we will focus on the critical value methods. If you focus on the p-values, let's go over the step here. The first step is the same thing as before. We have to determine the null and the alternative hypothesis in one of the 3 ways. So either you have the two tails, the left tail or the right tail. Now the null hypothesis again is always involve the equal side. So that when we talk about the two proportions, we assume them to be equal at first. So that is the null hypothesis. So the null hypothesis for the 3 cases here, they are all the same thing. The two proportions P1 and P2, they are equal. For the two tails, they are different. For the left tail, P1 is less than P2. Remember, the left tail, the arrow is pointing to the left. That's the way to remember. And if the arrow is pointing to the right, we have the right tail. Or P1 is bigger than P2. And P1 is just the population proportion for population 1 and the same thing for P2. After you determine the null hypothesis and the alternative hypothesis, the next step is we select a level of significant alpha. And this will depend on the seriousness of making a type 1 error. And usually we have the common choice for alpha to be 0.05, 0.1 or 0.02. Yeah, but the common choice is usually alpha is 0.05, which is 5%. Now for the p-value, again, you have to know the test statistics, and we can use this formula below here. Z0, this represents for the test statistic of the normal distribution. Z is the normal Z. Okay, so we take the ratio between P1 hat minus P2 hat, and take that, divide by the square root of P hat 1 minus P hat, and multiply by the square root of 1 over n1 plus 1 over n2. Now P hat again, this is a poor estimate of P hat. We got it from here, the poor estimate of P. So follow this formula, you can find the test statistic, and after that you can use the table A2 or the technology, the normal CDF from TI 8384 to determine the p-value. The p-value is just the area under the curve. If you have the two tails test, then it should be the sum of the area. If you have just the left tail, then it is just the area to the left of the test statistic. And if you have the right tail, it should be the right area of the test statistic Z0. Once you get the p-value, again the same rule, if the p-value is less than alpha, which is the significant level, or on it depends on how serious you make the type 1 error, you reject the null hypothesis. If the p-value is less than alpha, then reject the null hypothesis. If the p-value is greater than the alpha, then do not reject, or we fail to reject the null hypothesis, or the H0. Okay, so that's the p-value method. We can also use the critical values. We would repeat the same process, step 1 to 3 as for the p-value, and then we use the table A2 to find the critical value instead of the p-value. Now again, we have the 3 cases. If the critical value is inside the critical region, then we reject the null hypothesis. Otherwise, we don't reject. Okay. So let's say that this is minus z alpha over 2. This is the critical value, right? Now this is the critical region. If the test statistic z0 less than minus z alpha over 2 or greater than z alpha over 2, which is lying inside the critical region, then we reject the null hypothesis. Okay, let's go over this example. Decide whether the sampling method is independent or dependent. So in this case, we deal with the independent excuse me, independent samples. So you have to check whether the sampling method is independent or dependent, and then determine whether the response variable is qualitative or quantitative. Do women tend to select a spouse who has an IQ higher than their own? To answer this question, researchers randomly selected 20 women and their husbands. They measure the IQ of each husband-wife team to determine if there is a significant difference in the IQ. Because you want to make sure that woman selects a husband who has an IQ higher than themselves. So if you want to check that, you have to compare the difference between the IQ score. If we have a significant difference, that means the two IQ scores they are different in the value. That's why you should have a significant difference in the IQ. Now to answer this question, they select randomly 20 women and their husband. Okay, so let's see if this is independent or dependent. Because the sampling methods they select woman and the husband together. That means this is dependent, because once a wife is selected, then her husband is enrolled in the study, right? Because you want to select a wife and a husband. If you select a wife, a woman, then her husband has to go with her. So it's dependent. That is, the wife-husband team is matched up, and the response variable IQ is quantitative. Quantitative is is whether you have a quantitative is something that involves numbers. So because we talk about the IQ, so we talk about a number, the score. So quantitative is a measurement of something that involves a numerical values, and qualitative is something that is not related to a number, such as color, right? So in this case, because the IQ score is about a number, so this case is quantitative. Okay. Now this is an example for dependent. We also have an example of independent. Okay, let's say you are curious about whether the South California people and the North California people spend a different amount of money per month on movies. Now, it's very impractical to ask every people living in the Southern California and all the people living in the North California about their movie spending, right? You cannot just go and ask every single person. There's no way you can do that. It's impractical. So instead of you asking a sample, instead of you ask a sample of each, maybe you ask 350 people from the South and then 350 people from the North. Now in this case, the two group samples, they are completely independent and not matched up in the sampling process, right? Because you just randomly go to the South and ask 350 people, and then you add another 350 people from the North, and they could be anyone, right? Any person living at any places, right? So that's why they are not dependent as the last example, because once you select a wife, then the husband has to come along with the wife, because you want to check them, the IQ of the husband and the wife. So once you pick a subject, then the other one has to go with the first one. So they are dependent. But in this case, I don't care about who you pick for the North, and I don't care about who you pick for the South. Okay, so that's this an example for independent. Now let's go over the example for the hypothesis testing. In a study of police gunfire reports during a recent year, it was found that among 540 shots fired by the New York City police, 182 hit their targets, and among 283 shots fired by Los Angeles police, 77 hit their targets. Based on the data from the New York Times, we want to use a 0.05 significant level to test the claim that the New York City police and the Los Angeles police have the same proportion of hits. Test a claim using a hypothesis testing. So now you just want to test a claim between the two groups of police, right? So this is the two samples things. Now we know that the sample size for the first group was 540. So we have 540 shots of fire, right? And then the number of successes, so 182 hits the target. So X1 is the number of successes, so 182. And then N2 is the shots by the Los Angeles police, which is 283. And the number of successes was 77 hits. And alpha is the level of significance. Now after you have N1, X1, N2, X2, you can find the P1 hat, which is the proportion. You can find that by taking the ratio between the number of successes and the total number of shots. And you can find Q1, which is the complement of P1, right? So it should be 1 minus P1 hat. I forgot the hat here. And the same thing here, Q2 hat is 1 minus P2 hat. Okay. And after you found that, we do the requirement check. The sample proportions are from two simple random samples that are independent. So they just took the data from New York City police and also from Los Angeles police. They are not related to each other. They are not matched up. So it's good in this case. So they are independent. And we also check that there are at least 5 successes and 5 failures. And yes, we do see that the number of successes is 182 for the first population and 77 for the second population. So yes, they have over 5 successes and also 5 failures from here. So all requirements are good. And now we know that the original claim We want to test the claim that the New York police P1 and the Los Angeles police P2 have the same proportion. The same proportion means P1 equal P2. And if we see the equal sign equality, then we know that that should be the null hypothesis. Thus, if they don't have the same proportion of hits, then the proportion should be different. So if they don't have the same equal, then it has to be different one. So or P1 is not equal to P2, and therefore the alternative hypothesis should be P1 is not equal to P2. And in this case, because one is equal, one is not equal, this is the two tails, right? And before we can find a test statistic, you have to figure out the poor estimate and follow the formula here. You can find a poor estimate, right? x1 plus x2 divided by n1 plus n2, and that should give me the poor estimate for the proportion. And to find the test statistic, I follow the same formula here, and then I got all the values. We got all the values, so I just plug them in, and I got 1.907. Okay, so after we find the test statistic, we can use either the p-value or the critical value methods. Now, because this is the two-tail things, so we know that the test statistic is 1.907. So I label that 1.907, and then I should have another negative value of that, and the two area of the two end tails, one to the right, one to the left. So the sum of these two are the values, the p-value that we are looking for. Okay, or you just have to find one of the area and multiply by 2 because they are symmetric, right? I can use the normal CDF. Normal CDF give me the cumulative area from the lower to the upper bound, and then I multiply by 2. And I just use the one on the right side. So I use 2 normal CDF, and the lower one is 1.907, the lower limit. The upper limit is all the way to the right, or 10 to the 99. And that should give me 0.0565 and 2. Okay. Well, you can do this on the TI-84. You can just go to second vars. So let me quickly show you here. So second vars, and then go to normal CDF, enter, and then just hit the lower, enter the lower to be 1.907, and then upper, and then this is the mean to be 1, standard deviation to be 1. This is the default values, and then hit the paste one and hit enter, and it multiply that by 2 to get you the p-value. Okay, or you can use the table A4 to find the cumulative area to the left of the test statistic, and once you do that, you should get the same value, and it gives you 0.0565, and this value is greater than the alpha, which is 0.05 only. So if greater than alpha, we do not reject. Okay, so let's go to table A4 to make sure that I'm able to do that, to find a value. Okay, so table A4, oh, I think I make a mistake. It should be table A2 because we are talking about the z-score, right? So the z-score gives you the area to the left of that. So we see that I want to find the area to the left. So if you want to consider the area to the left, then pick the negative value. So minus 1.907, and that should give you the area to the left. so minus 1.907. So go to negative z-score, minus 1 point, so minus 0, no, 1.9, minus 1.9, 0.7. 0.7 is right here, so go down 0.0244. Okay, the thing is, this value is 1.97, right? Because you have make sure not to be confused here. 1.9 here minus 1.9. So minus 1.9 is the number 9 has one decimal to the right, and then 0.7. That means you add 0.7 to minus 1.9. So that means 0.07. So that's okay. Minus 1.9. You add the negative of minus 0.7 because we are talking about the negative z-score. So if you consider this value is already minus 1.9, and then we add the minus of 0.07, so that's give me minus 1.97. So just imagine that the zero here stands for the 9, so minus 1.97. It is not minus 1.907. Okay, so this thing is not the one we are looking for. This is minus 1.97, but we are looking for minus 0.107, 1.907. So we don't have an exact value for that. That's why in this case it's better we use the TI-8384 for that. So at first I was confused of getting the value from here, but then when I look back, minus 1.9 and 0.7 give me minus 1.97, not 907. Okay, so don't be confused about that. So we have to use the TI-84 or 83 to get an exact value for this case. Now to find the critical values, we know that this is the two tails. So we have z alpha over 2 and minus z of alpha over 2. And we know alpha is 0.05. To get alpha over 2, I divide by 2. And all I have to do now is I have to find the value of z alpha over 2. So I know that 0.025. This area is the alpha over 2. And this area here is also alpha over 2. So to find the z alpha over 2, remember table A2 only gives you the area to the left. So I know this is 0.025. To find all the area to the left of that, it should be 0.975, right? And then I go back to the z-score table. I look for 0.975, which is the area to the left. Yes, 0.975. 0.975. It should be this guy here. So go back to we have 0.975 exact, and the z-score should be 1.96 because we have 0.975 exactly, so which is 0.9750. and that should give me 1.96 for the z-score. Okay, so that is the critical value, 1.96, and because 1.907, this is less than 1.96, right? 90 is less than 1.96, so it is not inside the critical region. Therefore, we do not reject the null hypothesis. 8 knots. And yes, you can find here. I just show you. So the conclusion is that we don't have enough evidence to warrant the rejection of the claim that the New York bolus and the Los Angeles bolus have the same proportion. Okay, so because we don't have enough evidence to reject it. If we don't reject, that means we fail to say that the two proportions are not equal, right? Okay, so yeah, so do not reject the null hypothesis. Now we can also construct and interpret the confidence interval for the difference between the two population proportions. Recall that we assume the null hypothesis. We assume that the two proportions are equal. If they are equal, then we subtract P2 on both sides. We should end up with the difference to be 0. This means that we can construct a confidence interval estimate of the difference between the two proportions P1 minus P2 if the confidence interval does not include 0. We can have an evidence suggesting that P1 and P2 have different values, because unless they are not equal, then when you subtract them, they have something that is not equal to 0. If the two proportions are equal, then when you subtract them, you get 0, because they are the same thing. Subtract each other, they get 0. But if they are not equal, then the confidence intervals should not include a 0. So only when they are equal, then the difference is 0. And the confidence interval uses a standard deviation based on the estimated values of the population proportion, whereas a hypothesis uses a standard deviation based on the assumption that the two proportions are equal. When testing a claim about the two populations, we use the p-value or the critical value. But when we estimate the difference between the two population proportions, we use a confidence interval. So there's two purposes here, depending on how you want to make the claim or want to estimate the difference. Again, we have to do the requirement checks. The same thing as before. They should be the two simple random samples that are independent, and they should be the samples that have at least 5 successes and 5 failures. And then we use these two formulas to construct the lower bound and the upper bound for the two proportions. Okay, this is the critical value z alpha over 2, and then one we subtract the margin of error, the other one we add the margin of error. Now we use the same previous example in a study of the bolus gunfire reports. Now you just want to test a claim by constructing an appropriate confidence interval. So we have the same problem as before. We have the same thing, N1, N2, the same thing, P hat 1, P hat 2. We already checked the requirements, so we are good for the requirements. Now we also had the claims. The null hypothesis is when the two proportions they are equal, and the alternative hypothesis is when they are different. So this is again the two tails. and we found the pool estimate to be 0.315. We also know the critical value in the confidence interval here, z alpha over 2. We found that from here, z alpha over 2. Okay, so I also found that. So we have everything. We have everything here. Yes. So we have everything here. Z alpha over 2. Yeah. And then I got it from here, because we got the area to the left of that, which is 0.975, and the numbers inside here, the area. So this is the area. So you find the corresponding z-score 1.96. Okay, so that is the critical value. So after you got that, we follow the lower bound and the upper bound formula. We plug in everything we got from the two samples, and I got the lower bound and the upper bound, and one has this is the difference between them. So P1 minus P2 is the middle value of this inequality, and we do see that the difference between the P1 and P2 they contain the minus value and the positive value. So because the confidence interval limits contain the 0, because if you go from minus to positive, you have to go to 0. So there does not appear to be a significant difference between the two proportions, because they contain a 0. That means they don't have a lot of difference between the value. That's why when they subtract each other, they should be around 0. So that means there's not sufficient evidence to warrant rejection to the null hypothesis, from the null hypothesis that they are being equal for the proportion. Okay, the last objective is we can use the TI-83 or 84, and we can again make all the conclusion based on the technology. So I will use the same thing here again, the semi-sample, but this time we use the TI-83 and 84. So part A, we test a claim using the hypothesis testing, and then we test the claim by constructing an appropriate confidence interval. So the same data values, n1, n2, x1, x2, alpha. The same hypothesis testing here, the null hypothesis, the alternative hypothesis. Now to test a claim using the hypothesis test, we find a p-value. Normally, the technology gives you the p-value, and for the p-value of TI-84 or 83, we are using the test called a two proportion z-test. Alright, this is two proportion. That means two sample, and this is the z-score, the normal z or the z-test. So this one perform a z-test to compare the two population proportions. Okay, so in order to do that, we hit the start button, right? Hit the start, which is right here, start, and we go to the test because you want to make the testing, and we pick the two proportion z-test. It should be right here. Okay, two proportion z-test, option 6, and then after you click that, you have to input the value. Okay, so we input the x1, n1, x2, n2, and then this is the two tails, so we pick the difference between them. P1 is different from P2, and you hit the calculate, and it gives you everything here. The P here is the P value, which is 0.0566, and this is less than 0.0566. Okay, the p-value, this is a typo. This is not less than alpha, because alpha is 0.05. This is 0.056. So this is greater than. So if you have something that is bigger than alpha, we do not reject the null hypothesis. And you can see here, the same thing as we got earlier. We got something, right? 0.056. This is not less than alpha. This is greater than alpha. So we do not reject. And I do have a typo over there. Yeah, which is not less than. I'm missing the not here. Okay. And then part B. Okay. We test a claim by constructing an appropriate confidence interval. Now, instead of doing the two proportion z test, we use the two proportion z interval. So that should be the option B. So go back here, quit, start test, and then you go to two proportion z interval, option B, right? And when you hit that, again we input the same details that you got earlier. And because you want to have the confidence level, 0.05 is the alpha, which is 5%. 5% of alpha means 95% confidence interval. And 95% confidence interval in decimal is 0.95. Okay. So make sure you put the C level of 0.95 and hit the calculate. And it should give you the confidence interval here, the lower and the upper. And we do see that is the lower is the minus value, the upper is the positive value. And from minus to positive, there's a 0 in between. So yes, it does contain a 0. That means the two proportions, they don't have a big difference. That's why they do have a 0 in between. And yes, we are 95% confident that the difference between the proportion is between minus 0.0005 and 0.13036. So TI 83 and 84, they do have a program for you to find a p-value for the two sample proportion, and also find the confidence interval. So it's a great tool for us to use these days, so we can quickly check our process that we did earlier and make sure we got the same consistent answers for the two ways. Okay, so that should be the end of this section, and thanks for watching.